Hello everyone, we are back with another episode of Computer Vision Talks, and today we have with us Arman, and we'll be talking about his work on few-shot image classification, that is mixture-based feature space learning for few-shot image classification, which was accepted at ICCV 2021. And in case you guys have followed up through the mailing list, it was a follow-up from a work at ECCV 2020. Am I right?
Yes. Yes.
Awesome. Okay, so Arman is a PhD student at Mila, and he works on the ideas of meta learning, representational learning, and self-supervised learning in low supervision conditions. Okay, all of the interesting state-of-the-art topics. We look forward to your talk, Arman.
Yes. Okay. Can I start?
Yeah, sure, please.
Okay. Thank you. Hello, everyone. Thank you for the nice introduction and for the invitation. Yes, I'm Arman, and today I'm going to discuss about our paper, Mixture-Based Feature Space Learning for Few-Shot Image Classification. This work is done in collaboration with Jean-François Lalonde and Christian Gagne, two of my supervisors, which is published in ICCV 2021. Okay, so as we know that having a good and well generalized deep learning model, which looks very promising these days, the methods which are based on the deep learning require lots of training data sets. Okay, for example, in one of the benchmarks, which deep learning methods pass the human in that is image recognition. And for that case, for example, using ImageNet dataset contains over 40 millions of annotated data. This means that we have a significant human labor in terms of annotating or labeling the datasets. Okay, but unfortunately, this is not applicable in some of the real-world applications, such as the medical datasets or biomedical datasets, which gathering that much of the information and annotating that much of the data is looks for now impossible. So that's why the people are looking for an alternative solution, and one of these solutions is exploring other source of data which are imperfect, which could be a little bit imperfect, but we have plenty of them. So there are two, so we can investigate these data sets under several contexts of research, okay? But two of them could be, for example, using unlabeled data in the form of unsupervised learning. For example, I'm very interested on self-supervised learning nowadays, which we can have an access to unlabeled data and then investigate them in order to find a well-generalized model. Or we can also do self-supervised learning, meaning, for example, like transfer learning, okay? Having huge number of data, huge data set, we can build a model which can transfer knowledge to the other data set, which we have only few or even one example as the annotated data. Okay, this can be done in the form of transfer learning or domain adaptation. So under the context of few-shot learning, which is the topic of, which is the problem which we tackle on the paper, we wanted to build a model, for example, a network which is parameterized by theta, which can transfer the knowledge from the base classes. Okay, in the base classes, we could have more example, okay, and then transfer it to the novel classes with only few examples. For example, here we have one shot or one example in the novel classes. Here there is two differences with standard like image classification or generic image classification, which all of us probably know. Okay, so the base classes are distinct from the novel classes. So the novel classes are new classes, okay, which are distinct, and there is very few or even only one example for each of these novel classes. Okay, so in the literature, there are two training strategies to train a neural network, and we have either episodic training, or sometimes it's called meta learning or standard transfer learning, using a fully connected layer plus a metric learning based loss function. Okay, I will go one by one and discuss a problem with both of them and what is our solution then. So in episodic training, for example, or sometimes it's called also meta learning, we go over the base categories, and in each iteration, in each episode, actually, we sample a subset of class. Let's say that we have 100 classes, and we subset only 3 classes, which are shown here by 3 colors. And then from those classes, we also sample some support example or labeled data, and the query example, which we pretend that we don't know the label of these queries. Then the loss function is calculated based on the discrepancy between the support set and the query. Okay, for example, here in the idea of prototypical network is to just minimize the distance between the query and the mean of the support set. Okay, on the other hand, in the standard transfer learning, we have a fully connected layer at the end of the network. Okay, by the way, in episodic training, we don't have any fully connected layer. We are just try to adapt the feature extractor or the network. Okay, but in the standard transfer learning, which Chen et al. In 2019 in their iClear paper showed that, okay, with the use of good loss function, which has the metric learning property and deep backbones, we can reach to the state of the art and also reach to the results of these complex training strategy. Okay, what was the idea? The idea was that we have a weighted network at the end of the network or output neurons, and that W's are trained in a metric learning with a metric learning property loss, okay, with the loss which has a metric learning property. So this kind of training itself has 2 stages, training stage and fine-tuning stage. For the training stage, we adapt both classifier, last layer, and the feature extractor. For the fine-tuning stage, because unfortunately we have only few examples, we only could adapt a novel output layer, which is denoted here by n, which is for the novel classes. Okay, so it looks that we should fix the feature extractor, but that was the topic of our another paper, which is published in ICCV 2020, which we proposed a method which could adapt the feature extractor. Of course, for the episodic training, we have MAML, model agnostic meta learning methods, which we can have a quite like a very few updates, having very few examples. Okay, so so these 2 approaches. The problem with these 2 approaches, which we are going to tackle, is unimodal assumption. Okay, what is this assumption? Is that we are assume that we can represent the whole distribution with the single point at the feature space. What does it mean? Let's go through the detail. For example, in the prototypical network, as you can see, that the query is mapped to the centroid of the support set. Okay, this centroid, however, is supposed to represent the whole distribution of the single class, which is a little bit problematic, right? We cannot assume, I will show by some cartoon and also some solution for that, that having a unimodal assumption is a little bit strong. Okay, so in standard transfer learning, we have the same assumption. Why? Because per each class, we have only one weighted vector, which is differentiable, okay, at the end, which is like at the, which is connected to the output neurons, and we are aiming to learn that. Of course, I'm talking about baseline plus plus, which has a metric learning property, and it's nice for few shots. So that unimodal assumption, a naive solution for that
Hi.
unimodal assumption in the case of episodic training. Sorry, do you have a question?
Yeah, I do. I'm
Yeah.
raising my hand.
Okay.
Like, can you go to the previous slide again?
Yes.
So, like, this is not very much, I don't know. So, what I had to ask was that the use of cosine distance in all the tasks these days, be it self supervision or transfer learning, is increasing so much to measure
Mhm.
similarity between.
Yes.
Did you observe any drawback of using cosine distance, or do you think it is possible to use something else which might be overcoming the cosine? Because, like, I think cosine distance would not really cover the edge cases considering the graph.
Yes.
Did you? Yeah,
Yeah. Yeah. We can like sorry the cosine similarity. You mean right? Like for the cosine similarity, which we take the negative at that, for example, or we take the inverse of that to measure the distance. So for that, there are some options. For example, the prototypical network. It's interesting. I have some mathematical uh, like concept which shows that why Euclidean works better. Okay, but nowadays I agree with you that most of the paper are using cosine similarity. Okay, so for that, for example, margin is also could be better, like adding a margin based loss function, for example cosine plus a margin which could regularize the network. That could be a nice option. But beside that, the people are investigating some other metrics, like I saw in CVPR 23. I can send it to you. Like there are some other metrics, motion. I don't remember the name, but there are some new distances which people are investigating. Yes,
I see. Thank you. It would be interesting to read more about the distances as well, I think.
yes.
Thank you.
Definitely, the best part it would be like yeah, like the one of the promising things in future learning is to find the best metric. Yeah, I agree with you.
Exactly.
Okay, so it looks like that if we go with a naive solution for that unimodal assumption would be nearest neighbor. Okay, so in nearest neighbor, for example, instead of pushing the query to the centroid, okay, we can push the query to the nearest point, okay, to the nearest point instead of the centroid. Okay, so if we look carefully, while the prototypical network or the prototypical idea looks that it's underfitting, okay, from data representation perspective. Why? Because we assume that we can present whole distribution of a single class with a single point at the feature space. It looks like that the neighboring algorithm stays at the end of the spectrum, fitting data like fitting spectrum, and it is the overfitting. Okay, while the prototypical idea is underfitting, the nearest neighbor is overfitting, which is shown by the people, and I will show some of the results. Okay, for example, in that's why Allen et al. In their ICML paper, they worked on a very nice idea and they proposed infinite mixture prototypes, or IMP, for few shot image classification. Their idea was that instead of pushing the query to the centroid of the support set, first let's cluster the support set and then push the query, okay, to the nearest centroids, nearest class of centroids. I'm sorry. So for example here, for the green class, okay, so shown by supports are shown by the diamonds. Okay, we first cluster the points, okay, which for example in their case they use the dp means, which is kind of a k-means algorithm, but what the number of clusters are could be dynamic. The algorithm itself detects how many clusters do we require, and then query is just pushed to the centroid of the nearest cluster, okay, instead of pushing. So for example, in prototypical loss, the centroid would be something like here, but on the other hand, for the infinite mixture prototypes, which they proposed in ICML 2019, the query is pushed to the nearest cluster, So this cluster, we first cluster the support set and then move the query to the centroid of the nearest cluster. Okay, of course they have some idea that how we can use unlabeled data, okay, beside that. So, but unfortunately, their methods has some problem. The main problem was that they uses the dp-mins in a non-differentiable way. Okay, so what does this mean? It means that the model, the feature extractor, and the clustering algorithm are not synchronized. So we don't have an end-to-end model which could like adapt in a good way and find a better and informative feature space. Okay, so they use the classical clustering algorithm called the dp-mins in a non-differentiable way, and also they temporary perform clustering temporary inside each batch. Okay, the batch size could be small in an offline manner. Okay, so this means that we are already couldn't apply dp-mins on whole class points. So we are sampling the support set from them. For example, in each sample, I think they have 15. Okay, then apply the dp-mins on that 15 examples of the supports. They supposed to get a good clusters, the clusters of the points. Of course, like supposing that we can represent the whole distribution of a single class with the support set, then applying the k-means algorithm on that, or dp-means algorithm on that, would be a little bit too strong. Okay, so because for clustering algorithm, we know that we need lots of examples to work better. So to tackle these two problems, we propose a multimodal method that is fully differentiable, trainable in an end-to-end way, and captures the internal structure or mixture model of each classes without any classical clustering algorithm. So we are not using any k-means or dp-means type of the algorithms to find the mixture model. So if we look closer to the standard transfer learning and typical pre-training, that was with the episodic training. Okay, their method was based on the episodic training. Now I'm focusing on the standard transfer learning and seeing that how a typical pre-training is happening in, for example, using baseline plus plus, and which is proposed by Chen et al. I showed the paper. Okay, after moving on, for example, after moving a batches to the neural network and feeding forward through the neural network ends up with the embeddings, right? And those embeddings are vectors. For example, here for the bird class, I'm showing its embedding with the red rectangle, which is the embedding of that bird. Okay, so after feeding forward the examples to the network, in the typical pre-training of standard transfer learning, we know that we have, at the end of the network, we have base class vectors at the fully connected layer. Okay, so so here I'm using the idea of chain add-on. Okay, so we have single W's at the end of the network, which are single learnable components. They are trainable. Okay, like they are tensors, for example, parameters, which is defined by PyTorch. So they are differentiable, and we have a single point per class. Okay, so in the feature space, what's happening? I'm just showing these points with the stars. In the feature space, intuitively, we want to maximize the distance to get a good metric space. Okay, because we should maximize the distance, and this actually is done in association with training samples, which here I'm showing with the circles. Okay, so the idea of unimodal assumption now becomes clear. Why? Because we assume with unimodal assumption, we assume that we can present the whole distribution of these data points with the single point at the feature space. Okay, and that is a little bit big assumption. So, okay. So that's motivate us to propose mixture-based feature space learning. So I showed the problem, now I'm moving to our solution. Our idea is that how we can learn a mixture model based feature space which has a good metric learning property, and it is the combination of both somehow unsupervised and supervised learning. Why? Because inside each class I'm going to learn inside each class structure in an unsupervised way with a mixture model, and between classes I'm learning the supervised learning with the mixture based feature space learning which we proposed and accepted at ICCV. So we briefly call it as MixedFSL. Mixed here show the mixture based, FSL shows feature space learning. Okay, so let's see how it works. For MixedFSL, instead of having single learnable components here, we have codebook P containing multiple learnable components per class. So instead of having or reserving single vector or parameter, which is differentiable, we could have a codebook P, and inside that codebook, we have a sector. Okay, this sector is contains multiple learnable components for example, bird class. Okay, red here is representing the bird. In the feature space, okay, our method could train could learn these mixture models, okay, with association with the samples. Right now I'm showing only the codebook, okay, but it could learn both between and within classes, okay. So this is done in association with training data, okay. So we are learning inside classes mixture model of the classes and also in between classes in an supervised way. So our method contains two stages, two phases: initial training and progressive following. I will go one by one and discuss why do we need progressive following, for example, after initial training, and what are each components of each elements of initial training. Okay, let's first discuss about initial training. In the initial training, now I'm going a little bit more formal. For let's say that for class bird, which is shown here by red, we end up with the embedding zi, and I'm using z notation for denote the embedding of that bird, and we have codebook P, and row K, okay, is the subsector of row, capital row, which is, sorry, capital P, I'm so sorry, capital P, which is the sector, PK is the sector of P, capital P, which is the multiple learnable components for class bird, okay? So in the feature space, let's present these vectors with a single points. For the feature space I'm showing here is a cartoon. It is in very high dimension. Okay, let's just show them with the stars just for bird class and show how our initial training stage is working. So the first stage in initial training is to find, for ZI, is to find the nearest point inside that sector which is preserved for bird class, which is most similar, okay, with the use of cosine similarity, okay. We used cosine similarity to find the element which is most close to the ZI, and this circle is showing the training data embedding ZI. Okay, so let's say that we found that with the cosine similarity and yes.
I'm sorry. How did we find ZI in the first place? I think ZI is the perfect feature representation for a class, right?
The ZI is just the representation of single example. Okay, is for bird. It's
Okay,
just we
okay.
feed forward. Okay,
Okay.
is it clear?
Yes, so it is a single example of representation from the
Yes.
training data.
Yes. So this would be XI. Okay, this is the ZI, right? So okay, so I'm right now I'm going a little bit more formal. If for the ZI, is the embedding of xi through the network. Okay, we found the zi, and then we use the cosine similarity to find the u star I, okay, which is the is a single component inside that multiple components which is preserved for birth class. Okay, then with a loss function, we call it as assignment loss. We just minimize the zi to the u star I. Okay, so the loss function, which is right now I'm showing here, is the negative log likelihood of of the distribution of a pseudo label. This pseudo label vi is used. It's like one hot vector, and it's just one for the u star I, but has the size of p. Okay, it's not the size of the number of classes. It's the size of the number of classes multiplied by something, which the size of the code book. Okay, for example, in this case, the 5. Okay, if we have a 3 class, for example, we don't have only 3. Okay, we have 15. Why? Because we are using 5 per each classes. So we need to define a pseudo label to find the loss. Okay, so here we have an assignment loss with just negative log likelihood of 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 of, of of the example, giving the whole p. Okay, so this assignment loss maps zi to the u star I. Unfortunately, this could not be that much simple. Why? Because using only assignment loss, for example, could result in the case of a mini ImageNet dataset which contains 64 classes. I'm showing here the TSNE, only applying assignment loss with ResNet 12 on mini ImageNet. Okay, these are the mixture components. No examples are here. Okay, the TSNE results shows us that only single component are survive, or the others are dying or became deactivated. Okay, like here you see the big clump. These are the components from all classes which are became deactivated using only assignment loss. Okay, so this means that only u star I, because everything is just dynamic. Okay, we are learning the whole training procedure with a stochastic gradient descent, so it just pushes the rest of these components to became deactivated and only picks one after few iteration. Okay, so here you see different colors are showing different classes. So for each class, unfortunately, only single component from that code book P like became activated, and it rebacks to a unimodal assumption, because we only have single component. Okay, the others became deactivated. That's why we add another loss function called diversity loss, and it in unidirectional way. I will tell in a minute why we need unidirection here. In a unidirectional way, it maps zi to the center of all the component reserved for that class. Okay, so for example, here we have 5 components. Okay, we compute their mean. Okay, here I'm showing the compute the mean of that class, and then we build that mean sets of I could say meta components, and then push zi to its corresponding set. Okay, so this is, as you can see here, we have a one directional arrow, meaning that only we adapt neural network or feature extractor, and we don't backprop the error through the p. That's why we have here the stop gradient. Okay, when we define the diversity loss with the negative likelihood. Okay, that's why we have stop gradient. I will go and discuss why we need that stop gradient now. Okay, so here just stop gradient. Don't let the gradient flow through the p. So why? Because if we don't have that stop gradient and we update both p the code book, okay, the mixture model, and the neural network, then all of the points from the same distribution will collapse and we would have single mode again. Okay, it's very complex. I'm sorry, I'm trying to just show it in very simple way, but just if we don't have that stop gradient, okay, then all of the points belonging, for example, to this class became collapse and we have single point. Why? Because computing this mean intuitively or indirectionally tells that all of these components should be their distance also should be minimized, and the code book and backprop do its job and minimize all of the points distances, and we just end up with single point. Okay, however, with that stop gradient, now we can learn the mixture model per classes, as you can see here, in a good way. So right now, at least the TSNE of mixture component using ResNet 12 and mini ImageNet, each color showing one classes. So in mini ImageNet dataset, in the training time, so we have 16 4 classes, and here you see the 16 4 classes with different colors. Okay, so right now we learned the mixture model of that classes in a good way with the combination of assignment loss and diversity loss plus stop gradient trick. Okay, and but up to now, I only showed you the TSNE of the mixture component, that P, okay, the code book. But let's see some examples. Let's see if the examples are also are mapped in a clear way with those components, okay? And here you see the examples. Okay, the diamonds again are the mixture component element at the initial training of our MixedFSL, and these circle, which are a little bit dye, which they have light colors, sorry, so they are in the background, and we are showing that the feature space are not that much informative because they are not aligned with the components in a good way. Okay, so there is a problem here. So let's see what is the problem. Actually, we are discussing the problem in the main paper in a good way. So if you are interested, please read that part. Okay, the problem is that in the initial training, having two loss, it seems that the competition starts after some times, okay, after some epochs which we train the network. And why it happens? For example, if we have zi and this is u star, and there is a neighboring component for that u star I, after that zi gets closer to all of the components, it seems that having a competition between U star and its nearest components is probable. So we could have a competition between them, and that competition could destabilize the training. So while in one iteration, Z star wanted to map and capture to minimize the distance between UI star, in another iteration, it could change and move toward its neighboring, okay? Because in that one could be the closest one, and that competition is destabilizing the training, okay? So why? Because again, we are using stochastic gradient descent, so everything is dynamic. Okay, we are just sampling, so sampling a subset of the data set. So here the destabilization comes from there. Okay, so for that we proposed progressive following, the second stage. In the second stage, the aim is to don't use the diversity loss, because that diversity loss seems that it destabilizes the training. Why? Because if we should have something to tell that, okay, zi should map only for u star I, it should not go through the center and give more freedom for that components to act independently. That diversity loss was the problem. So for in the progressive following stage, okay, in the second stage, we have a sort of a student-teacher relation to solve that problem. Okay, so for xi, the input of the input, for example, the input could be the image of that bird. We have now we have a copy of the feature extractor with with parameterized with theta prime, and that theta prime is best validated network with its codebook p theta. Sorry, I should notice here. I should put here the rho prime, something like that. Sorry. Okay, rho prime, and this is, sorry, p prime, and this is p. Okay, so that prime shows the best, okay, the best thing which we found, the best parameters which we found with the validation set. Okay, so here the best validated network became this teacher, and the current network is try to learn with the guide of that teacher. Okay, so the best validated network offers pseudo label. Now the diversity comes from the teacher because it learned something during the initial training. It learns which component should be active and which component should be, for example, mapped to what sample. Okay, then that fixed best validated network becomes teacher to provide the pseudo label for the student, and then we have progressive following loss, which is nothing but the assignment loss with the pseudo label which comes from the teacher. Okay, here the teacher only offers the pseudo label, and this teacher, okay, in order to be actively doing its job, is updated through the time by best validated student. Okay, so we updated with the best validated student through the time, and there is a temperature factor in our softmax function, likelihood function, which try to just push the x to the z with 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 more forces. Okay, when we decrease the temperature, it says that just in softmax function, when we decrease the temperature, it just pushes the embedding zi to the u star with more okay, in sharp way. Okay, in more in hardly. Okay, so if we saw the effect of, if we just wanted to see the effect of progressive following, after initial training, as we saw, the examples in the background shown by the circles are not well aligned with their mixture component. After progressive following, however, you can see that it seems from TSNE results that the feature space are learned in more informative way, and we have clear boundaries between the classes, and as you can see, the distribution are well separated. Okay, and here the diamonds are just the the mixture components, and they could have dynamic numbers, because after initial training, okay, let's say that our method is end up for one class can be represent its internal distribution mixture model with 5. For another class it could end up, for example, with 8. Okay, so here you see the mixture model of each classes. Okay, for the evaluation, we evaluate our method MixedFSL using 4 different datasets and 4 different backbones. For datasets, we used mini ImageNet, which is a part of full ImageNet with 100 classes, 64 for training, 15 for validation, and 24 for testing. Okay, during the test time, we don't go over the test in 20 ways. Okay, in the literature, mostly the people are testing in a 5-way, meaning that if we have a 20, we are defining, for example, 600 episodes. Okay, in a 5-way, we go through that 20 and we sample 5 of that, and then we test the generalization performance, and that could we can repeat that for 600 times, and then we average that, and we also show the average results. Okay, beside the confidence intervals. We have a tiered ImageNet, again a subset of a full ImageNet, but this time with more than 600 classes, sorry, 700 classes, and we have FC100. It's still the benchmark is smaller than tiered ImageNet. It's only 100 classes like mini ImageNet, but for tiered ImageNet it's good. Like we have over 700 classes. And also we have CUB dataset, which is the BERT dataset for fine-grained classification. So we interested to see what happen if the dataset is fine-grained, meaning that all of the classes are from same animal, for example, okay, from bird class. And for the backbone, for the feature extractor, we used Convo4, ResNet 12, Wide ResNet, and ResNet 18. Here I'm showing some of the results, but we can go over the paper and discuss the other results too. Okay, in mini ImageNet dataset using ResNet 12, okay, we are showing here in 5-way, meaning that we have a 5-class classification problem, okay, in 1-shot and 5-shot. We just like the literature, okay. So here you see the baseline and state-of-the-art methods. The state-of-the-art is coded by blue, and our method MixedFSL, which beats the state-of-the-art and bolded. Okay, so here you see that unfortunately in 1-shot, okay, although it's bold, but it could not pass the state-of-the-art with big margin. Okay, so it is in 5-way having yes, we are averaging over 600 episodes, but still the difference is not that much. Okay, so but in 5-shot, we can say that near half of a percent we are over the state of the art, which is coded by blue. It's not too much big, but it's still acceptable. Okay, in tiered ImageNet with a lots of classes and a lots of samples, here you see our MixedFSL in both ResNet 12 and ResNet 18. By the way, for mini ImageNet, we evaluated with other backbones, and there are in the paper, and we can discussing them if you have a question. Okay, I'm just showing some of the results here. Okay, here you see the backbones with ResNet 12 and ResNet 18 for tiered ImageNet, and our method, which is last row in both of the cases, passed the state of the art in all of the cases, and these state of the art are highlighted by blue. For example, in 1-shot using ResNet 18, our method passed the state of the art by 3.53%, which is the big margin. Okay. In FC100, okay, our method again shows some boosts over the state of the art. For example, in 5-shot using ResNet 12, it beats the state of the art TADAM, okay, with 4.60% accuracy. Okay, we also tested in CUB, fine-grained classification problem, and cross-domain. Okay, I will give you. I will discuss what this cross-domain mean. But in CUB, in 1 and 5-shot, seems that our method couldn't pass the state of the art in 5-shot. Yes, in 1-shot it could pass, but in 5-shot it stays below the state of the art. And this is actually very interesting. Why? Because it seems that in the fine-grained classification, when we have a good mixture of classes, because all of the classes are from same animal but different types, okay, so it seems that our method does not have any benefits in that cases, while in 1-shot it's good. Okay, however, during the like cross-domain adaptation, or having like training on mini ImageNet and testing on CUB in 5-shot, it shows that it gains some accuracy over the state of the art. Okay, so for example, that one is 1.74% over the state of the art in cross-domain adaptation. This cross-domain again is trained on mini ImageNet and tested on CUB. Okay, it seems yes. Okay, so I'm moving on. Also, we tested on more way, meaning that not only 5-way, which we discussed, okay, in both ResNet 18 and ResNet 12. This more way, at that time, I couldn't find in the literature more results in ResNet 12. That's why the ResNet 12 is at the end without any comparison. However, for ResNet 18, in 10-way and 20-way, meaning that we have more ways, okay, like instead of going and sampling only 5 classes, for example, in the case of mini ImageNet, we are using all of that 20 classes from mini ImageNet dataset. Okay, in 20 ways, we beat the state of the art, and also like in 10 ways. Okay. Before ending the presentation, I wanted to show this dynamic of training, which shows us why do we need these two, initial training and progressive following, from validation set accuracy perspective. Okay, we saw from TSNE, but let's see from some plots. Okay, so for ResNet 12, here you see the epoch versus validation set. Okay, and as you can see, each okay, we have 1-shot which is colored by blue, and then 5-shot which is plotted by red, and we have a cross line here, which this cross line shows us where the method, our MixedFSL, is switched from initial training before that cross to the progressive following, okay, after that cross. And these bubbles, okay, these circles are showing when we update the best model in the early stopping mode. This window, okay, between the bubble, okay, the last bubble in the initial training, and the starting of the progressive following, is the window or early stopping, which set it to 15, I guess, to say that if we don't have 15 number of updates, then change to the progressive following. Okay, as you can see in the 5-shot, okay, the method is not boosted that much, okay, in the ResNet 12 after initial training, but in the 5-shot we have a good boost, meaning that progressive following helps. And however, if we saw ResNet 18, in both cases, as soon as the progressive following starts, okay, we are seeing that some like leap or some jump in the performance. So that comes from that teacher student which stabilize the training, okay, and try to build a more informative feature space. By the way, the plots are obtained through the validation set, not on 600 episodes. Okay, so I would like to say thank you so much for the invitation, and thank you for the attention.
Thank you so much, Arman. Yeah, like it was a very informative session, and yes, you explain things so calm and so nicely. You should definitely consider teaching as an option sometime.
Thank you.
Yeah, it is very nice, all the background information, and I'm very thankful to the audience for joining, although little late, because like usually like I used to host the talks in India, and now I've moved to Montreal, and I'm choosing time zone on basis of Montreal, but it's too late for the Indian audience to catch up. Yeah, but so yeah, people were joining and moving and messaging that we'll watch the recording, but thank you for the ones who decided to stay.
Yes.
You can drop in your questions in the chat box, and I'll let you unmute you and ask your questions. But till then, till you have questions, I have a lot of general PhD related questions that I prefer asking everyone. Is that okay? Shall I start, Arman?
Yes, I don't know.
Okay, awesome. So the first one would be how like how long did this paper take you to complete, and what were the new things that you had to learn or read about for this paper, for this work?
Okay, okay, yeah, that's very nice question. Actually, this project, it was about 1 year. Okay, like I spent 1 year like working very hard on the problem because it was not easy problem. We end up with many problems, like for example, moving from inside that initial training, figuring out, okay, right now we need two loss functions, like takes 2 months. Okay, it was not that much quick. And then, for example, finding that, okay, we need now progressive following, takes with a lots of meeting with my supervisors, which they are really kind. It takes, like for example, 4 months, okay, to figure out that right now we need that progressive following. Okay, the method still can make sense, but then the method, we know that the method can make sense, but when we were working on that, we sometimes I was frustrated because I couldn't catch the state-of-the-art results. And then we figure out, okay, let's analysis with TSNE. I would say that it takes 1 month, okay, and it was not that much easy, but I really enjoyed while working on that project, and I really learned a lot of things.
Okay. There's a question in the chat box related to the paper. Shaman is asking, could you explain the intuition behind diversity loss? Is that why map it to the center?
Okay, here, okay, I will go to the presentation, right? Okay, diversity loss. Why it could map to the center? Uh, because if we map to, okay, because we should tell, like in not directly, in an indirect way, we should tell the feature extractor. We don't, we don't want to adapt the code book, because as I showed you, the adapting the code book with results some collapsing. We tested a lot of things, but the center, like pushing the zi in indirect way to the centroid of all components, is telling to the network that adapt zi in such a way that can activate it, the other components. Okay, because here the problem is that if we just only use assignment loss, then the other component will be deactivated. Okay, that's why we are using the diversity loss by pushing to the centroid, okay, of that components. We are telling the neural network that give me, like give the other, give chance to the other components also became deactivated for the other examples. That's why we just push it to the centroid. But here again we have using the step gradient. I don't know if you were from the beginning of the presentation, but if you
Yeah.
have any question, I can also go and discuss it.
I hope that answers your question, Shravan. You can also unmute yourself if you want to ask me questions.
Yeah, that answers. Could you also explain the teacher forcing part, like how you got that idea?
Okay, teacher student. Okay, so we
Yeah.
need okay, yeah, that's also, so we need a technique. Okay, we need a phase to don't use the diversity loss, because as I discussed here, okay, so the problem happens when zi became closer to not only u star I, but also in the neighboring component. Okay, so that part, like the neighboring, plays rule here, because the diversity loss. So why it is called diversity? Because it diversifies our decisions over the components. Okay, so so we don't need that diversity. Okay, instead we only need assignment loss, but that assignment loss brings some problems which I discussed. Okay, however, in order to don't use that, we need some fixing labeling method. Okay, something to fix the neighbor, like the labeling. And that fixing the labeling, which it uses the diversity which is trained in the initial training. Okay, it used it. So here is the idea. The diversity. So this teacher model, okay, tells us, okay, the diversity which I learned during the initial training was the good one. Okay, let's move on without the diversity loss and just push the example with the assignment loss. The teacher is telling that I will provide you the label. You just force zi to the nearest component. Okay, that's the solution which we found.
My one question is that how would it be different if we did not have this teacher? If we
Yeah.
directly use the earlier computation only, um, saying that let us assign it, since the diversity loss has already been learned by the model and that is reflected in the embeddings, let us just
Okay.
assign it to the nearest u star i's and then train it instead of this teacher.
Okay, so you mean that if we don't have that fixing label, right?
Yeah.
Okay. That's a very nice question. So if we don't have that teacher, okay, we will immediately back to the single mode, okay, because of this problem. I will show you. Oops. So because of this, okay, with only using assignment loss, okay, immediately with, okay, it doesn't matter, okay, because gradient descent, okay, is just to try to find the best solution, okay. In this case, the best solution would be nearest component, okay. So because the training is dynamic, yeah, we can learn something during the past, but if we just push to the nearest component, then one of them will be picked and the other will just become deactivated. Is it the
Okay, so it acts as some kind of yeah, I get it. Yeah, it acts as some kind of an instructor to say that okay, don't okay, you have to go to these different labels which I'm giving you instead
exactly
of just collapse to one. Okay,
exactly that's why it's called teacher, because it provides label. Actually, it is
yeah.
pseudo label, I would say, because it is just the true label is the label. For example, we know that it's belong to bird class, but we don't know if it belongs to which component inside that mixture model.
Um, this is a bit maybe unrelated, but um, how did you actually get an idea to use something like this? Because like was it already in the literature, or was it something novel you came up with as you went on experimenting with new methods?
Okay. So at the beginning, honestly, I at the beginning of my PhD, I was really interested on mixture model. Okay, I worked a little bit on that. Then I don't know, for some reason I put aside, and then I started to work on associative alignment idea. Then I see this nice paper from MIT group at the ICML, okay, infinite mixture prototype. I was at that time, honestly, I was doing something similar. Okay, I was training the mixture model with nearest neighbor. I was knowing how it limits. However, their method, infinite mixture prototype, was much better than my initial idea, okay, because it was using dp means, I was using k means, it was not working. But dp means has this nice property of don't deciding the number of clusters, and also they did it in very informative way. However, when after doing my ECCV paper, associative alignment, I read this paper, which motivated me to go further and propose the method without any classical clustering algorithm. So it learns, it is an end-to-end model. Yes.
Thank you.
Thank you.
Great presentation, by the way.
Thank you so much.
And a great discussion session as well. I could not come up with those questions. Those were nice questions.
Thank you.
Thank you, Arman, for answering
Thank you
them.
so much.
I have got 2, 3 more questions, and I'll make it quick because we've already taken a lot of time. One would be, since you're towards the end of your PhD, and because in my circle, like some of my friends who have also joined, want to switch to a PhD immediately after their undergraduate. So, what are, say, 2 to 3 things or 5 things, as many things as you would want, that they should know about a PhD before getting into one?
Okay, so one of the things which I would say is that knowing the how like how can I say, knowing what would you like to do. Okay, it's not the matter of being in a strong group. Okay, let's say that in in I don't want to give the name, but let's say that I'm in a very good group, but I don't like the problem. That is the cause of problem, I think. Like I would say that being in a group which with a topic which you like it is the most important thing. Like the topic you should choose is will stay for 4 years. And one of the things which like my supervisor teach me is that like the things like like how can I say, I don't. I wanted to choose the right words because, like the words should have high quality, and we should not like count for the quantity. Okay, and this was the things which my teacher. I hope that I did that, but they tried to learn me. And one of the other things was that okay, there are some times which, including me, that I wanted to change the topic, for example, at the middle, which at that time, I think the good thing is just to follow the experience of the advisors. So two of my advisors told me that you should stay, for example, for this problem. Okay, I worked on that for several months, and then I figured out that it's not working. But Jean-François Jeff is very like a friendly guy, and Christian told me that you should work on that, and finally we got that. So I mean, perseverance is very important, like hard working, and the topic which you like it. At the beginning, as I think we discussed, like I started with another topic, and then I figure out that fuchsia learning who is the things which like interest me a lot. Yeah.
Interesting. Okay, last question. So, um, now that I am a graduate student, I see two schools of thoughts. One where one person is indulged into multiple projects, and yeah, so chances of a publication are quite frequent, because if you're in 4 things, one of them will end. And the other way is that your supervisor is asking you to take like 6 months, 7 months to do a background survey first to identify the potential flaws. So
Yes.
while the one where 6 or 7 months are just being invested into understanding the problem can be a bit slow, like if you want to get into publication mode very quickly.
Exactly.
Yeah.
Exactly. Understanding the problem itself, I think, is a little bit important having the solution. Okay, because after understanding the problem, I would say finding a solution became easier. Okay,
I see.
so that understanding the problem, especially in our domain, which competition is really high, is not easy, because there are lots of papers which we should learn, and also hands should be on, like we should like implement something. So six, it doesn't matter the time. I think the important thing is to understand the problem itself. Yeah.
Right. Okay. Interesting. Okay, that was a lot of information. Thank you so much. I'm
Thank you
glad to
so much.
host you.
Thank you
Yeah.
so much for the invitation. Yeah.
Thank you. Thank you. Arun. I'll be uploading the recording on the YouTube and sharing the link as well. And also,
Sure.
guys, don't forget to check out the code base. So I was yesterday going through the code base for the paper, and it's pretty sorted. At least you have listed out the dependencies needed to be installed and everything. It's pretty clean and sorted. Yeah, I really appreciate the code
Sure.
base. Thank you.
Sure. 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 Sure.
Thank you.
Thank you so much. Thank you.
Okay. Good day, everyone. Bye bye.
Have a good day.